Welcome back to the hyperbolic coding chamber. We are back once again. It is unclear what day it is, but it is clear what we have to do. Fortunately, we finished the torture chamber that was yesterday. We had to watch basically a bunch of videos on how a heap works, but I had watched them once on normal speed and then once on half speed to make sure I understand it. Today is the day where we try and implement it. They haven't told us anything about the implementation because in Python they just expect us to use heap q, but there's no way we'll learn it if we don't do it the hard way. So unfortunately, we're locked in here, and this is a necessary evil to accept. So this session is probably just going to be us struggling through heaps of struggle to see if we can make sure that a heap makes sense. I'm not exactly certain if we're going to rewatch the video on half speed because it felt more like a brainwashing. It felt more like a brainwashing chair than actually learning. But maybe that's what learning is. Fortunately, we have a problem already queued up to solve, so hopefully it'll make sense then. So, as we can see, we have about 285 problems done. Maybe. 286 considering the heap problem. Progress is slow. I think we're going to slow down just a little bit because we have to figure out this heap garbage. Once we figure out this heap stuff, from there, if ChatGPT hasn't forced us all into enslavement, maybe we'll be able to finish all the problems. But yeah, I would say we're almost not even half. We're about 35% of the way there, because then we'll be halfway done. So that would be pretty cool. But we'll see if we ever get there. Unfortunately, we have to slow down a bit and learn some heaping stuff. But yeah, learning kind of sucks sometimes. But I think we've been doing problems, which is more about struggling. But I haven't sat down to actually learn and see how. Actually learn in a little bit. So I'm a little bit opposed to it. So the heap problem, or the heap thing we have going on here, hopefully will help us learn in the future so that we stop resisting all of our pain. So hopefully that makes sense. That being the case, I made a realization yesterday working on the game. I was struggling to work on it because I was making something that I expected someone else to play. So maybe there's some overlap with struggle when you're making a product versus when you're making something you want for yourself. So I make a lot of small apps for myself that I use, and I think, this could also be useful to other people. And I think somewhere along the game I lost that, and it just kind of devolved into absolute nonsense because I was adding features that I wouldn't use or I didn't enjoy, specifically to appease other people. So maybe there is something here, like in My Hero, where you can win to save and save to win. And in this case, maybe we can do something where we finish to create rather than create to finish. So the whole point of finishing would be that we'd make it for ourselves so we could get through it and make something that's actually enjoyable. And maybe we'll add like 10% non-dopamine action so that's palatable to other people. But I think what I was doing before, it went from being a project that I actually wanted to work on to like a product, which is fine. But maybe if I make it for myself, maybe it is still a product for other people as well. Maybe people just like me, but I'm not really certain. But hopefully it'll make more sense later in the week. So that's where we're currently at. I also realized this channel is kind of another incarnation of that. I like the longer form content that Ivan Jurek makes about squatting every day. And so this is the kind of content that I make. Just pretty much the same thing, except I'm showing what I'm doing as well. And I'm realizing I've been struggling to make the devlog as well because I don't really watch devlogs. So that was kind of the nutty part to me. So maybe we need to find something else to make. I like the daily aspect. It's simple, it keeps me motivated, and it works for me. And I feel like a caveman because I feel like I keep relearning the same lessons. So maybe we need to write these down somewhere because I feel like I learned the same lesson a couple of months ago and we're relearning it again. And I think it was in a LeetCode video called "Do What Works for You" or something like that. And this works for me, so maybe that's what we'll keep doing. That being the case, we can't stall for the problems any longer. So I'm gonna see if I can make this implementation of a heap make sense based on all the brainwashing from earlier today, from yesterday, and then yeah, hopefully we can make it make sense. If we can't, we'll try and see if we can get some help. But if this is something you're interested in, you should join the Hyperbolic Coding Chamber. It's a chamber designated to be a hyperbolic chamber to quickly progress through the coding trials. If you make it to the end, you'll be rewarded with all of the entirety of the Discord's assets. So pretty cool. Also, we're gonna raffle off the channel. We're gonna raffle off the channel at the end to a random Discord user. So when we complete the challenge, which is likely which is probably the end of this year. So that being the case, I think we're gonna stop there and jump into the work. So we have kth largest element in a stream, which is a problem we worked on where we pretty much needed access to a heap, but we didn't do it with a heap. We did it with like a ghetto version of a BST, which was super slow. It was actually slower than just sorting with n log n time. So what we're going to do this time around is we're actually just going to use a regular heap that we learned. I forgot to switch screen. We're actually just going to use a regular heap this time, and hopefully we can actually implement it, and hopefully it'll make sense. What we need access to first is a binary node, and we're also going to need access to be able to swap. There's a lot of shifting that happens with the heap, so when we implement it, we're probably going to need access to our parent node. So we're going to keep that. We don't have to worry about extras because in the heap you can actually have equivalent values as well. So that actually does work out. We'll keep the B node class. We'll keep insert, and we'll keep print as well. Yeah, we'll keep print as well, except when we print it, instead of printing it how we're doing it here, we're gonna print it passing in the root B node, and we're just going to do a BFS instead, which is going to rely on there actually being a queue of B nodes, which the root is going to be a part of. We're going to say while q.length does not equal 0, we're going to say node is going to be equal to q.shift. And then we're going to say if node.left, we're going to push on q.push node.left, and then additionally we're going to push on node.right if node.right exists. And then we're just going to make sure to do node.print the value, and then I think this should basically print it. I don't think we'll need this build function anymore. And then from here, I don't think we're going to need this find next largest node function either. From the constructor, we're going to use this to test if any of our code actually makes any sense at all. Instead of root, we're just going to have a heap, which is just going to be a heap. It's actually going to be a min heap. Yeah, it's actually going to be a min heap, because if it's a min heap, right? We want to have access to the kth largest element. If we want to have access to the kth largest element, if we make a min heap where the top value is going to be the smallest, we can actually just make sure that the heap has k values in it at all times, and if it ever exceeds that, we can remove the smallest value, making the top value the kth largest value. So we'll create a new min heap with a constructor like so, and we'll create that later. And then for kth node, we won't have access to that anymore. We won't have a root. For every node in nums.length, what we're going to do is just do this.heap.add, and we're just going to add the number. And in fact, we can probably just do something like for const num of nums. And the add function we're going to make is supposed to work in and then we'll do print. Actually, we can just do this.heap.print. And from there, I think we should be fine. I think we can basically remove everything in this add function. So we have a B node, right? And print and insert. We'll change insert to add, and it's just going to literally just be a value, right? And then now we just need to actually create the min heap. So say class min heap, right? We'll create a constructor. I don't think it's important that this has any particular value, but it's going to have a root node, which is going to be a B node. Actually, it's going to be null. Yeah, I guess we don't really need access to a constructor. And then we'll move this. We're going to have the add function. For some reason, not every line is being pushed over. So we have this add function. We're just going to return 0 for this when we run it. It's going to give us the wrong answer, but this is fine. This.heap, we should be able to say this.heap.print, and we shouldn't need access to a root node because the root node should be and we'll just say if the root doesn't exist, we'll just return. So we have a value, right? The first thing I have to do is make sure that I think there are two most important properties the videos kept hammering into our brains. It has to be a complete binary tree. So we're always going to be working with the rightmost bottom element. And then we have to make sure that each node is less than or equal to its children. Right, so if we want to add into the tree, how does it, so apparently add is supposed to take log of n time. If you're inserting at the end the bottom rightmost element, maybe you have to keep a pointer to that element. If you do, then the shifting that takes place to make sure that the node is less than or equal to children would take log of n time. So maybe you need access to the most leafed node. How would you even keep track of that? How would you even keep track of it? It doesn't even make any sense. Yeah, I don't understand how is this? How is this possible? If you need to insert a node in the bottom rightmost element, how is it even possible that this takes log of n time? If we did post order, no, if we did in order, we would always get the bottom leftmost child. Yeah, this doesn't make any sense. Maybe a heap implementation is actually crazy. How? I thought if we did in order, we could get to the bottom leftmost node. What if we started from the beginning? If we started from the beginning, if we add one into the node, we know that the leaf node, or the bottom rightmost node, would be the node that we're currently on. If we added another one, we add a left child. If we added another one, we add a right child. We don't want to move the node when we add them. We want to make sure that it doesn't have two children already. Now, what if we added those two nodes to it, and then we made sure that the next leaf node was the node to the left, and it technically would be. So let's say we add two children to that and two children to that. The problem is the next leaf node would actually be if we did do it that way, we would basically keep a list of the next bottom rightmost node. The problem is if we delete a number, we always remove from the top. If we remove from the top, then it feels like the leaf nodes get messed up. But what if we played with this just to see? So we have bottom rightmost node, right, which would be an empty array. We have a heap, right, that's going to start with the value 1463 negative 1. So we add 1. We see the bottom rightmost node is 1. Right now we want to add 4. To add 4 to the bottom rightmost node, we check if the bottom rightmost node doesn't have two children. It doesn't. right? So we would add a leaf for 1, and we would add 4 here, right? Now let's say we add 6, right? It doesn't have 2 children yet, so we go like this, we give it a 6. Now the next bottom rightmost node should have been 4, and the next one after that will be 6. Now that it doesn't, so let's just say we had done that, we placed the bottom node left, right? We'll say this is the next bottom rightmost node. So maybe we add them in reverse like this. Right, we added 2 for 4 and 6, so we pop 1 off. Right, now we know the next bottom rightmost node should be 4. And this is not a BS, and this is not a heap yet, but we'd have 3. We'd say the next bottom rightmost node would be 3, which is kind of working, right? Then we'd add -1, which would go here. We'd say the next bottom rightmost node would be -1. Right now 4 doesn't have 2 children left, so the next bottom rightmost node would be 6, which actually does work pretty well. We'd add 2 for that, and the next one would be 3. Now let's just say we want to remove 1. We want to remove 1, right? Then we know that the bottom rightmost node replaces that topmost element, right? So the number at the end, so we, oh, this is perfect. We end up actually having instant access to the bottom rightmost node, so we could remove -1 here and place it up here, and then do the shift, and then we could remove it from the front. So it looks like we'll have a history of B nodes So when we add a value to the list, we can check if root, if not root, right? Then we'd like to do some specific code. Or if not this dot root. So if not this dot root, then we'll say this dot root is equal to a new B node, which will get the starting value. What's the constructor look like? We have val, left, right, and parent. So the value is going to be val. Parent is going to be null. And actually everything's going to be null basically. And then we'll say this dot history. And it might actually better just say BMR, bottom rightmost node, so BRMN. It might just be better if we just say bottom rightmost nodes. It's going to be an array with this dot root in it. Now, if this dot root exists, is another case, right? If this dot root exists, then we need to grab the bottom rightmost node, the first one, and say if BRMN then we want to place it there, right? And so where we place it is if brmn.left doesn't exist, I would say brmn.left is equal to new B node, where the value would be val and the parent would be brmn. And we'll copy this and we'll say and it actually might just be easier to do the other case first. So we'll say if brmn dot left and brmn dot right if that's the case, we do some work, and then we can actually just expand these out here, and then these just become else ifs that look a little less messy. So if brmn.left and right are already set, then what actually happens is you take those bottom rightmost nodes like 1, and then we would shift it off of the front and take the next one, which would be 4. So we take it off the first, we take off the front one, which is brmn. We can basically copy this line here and turn this into next. And then we'll say if it's the next one, its left one can't be filled in. Right? If the previous ones left and right are filled, this might be where it gets messy. If the previous ones left and right nodes are filled, right, the next one would be 4, which we take off the front, and so we have access to, which is next. We'd like to add it to 3 here. Actually, this is more confusing. So we'll just say next equal to new B node with the value, except the parent actually no, I think this is fine. If we just call this new node, what happens in here is that new node dot parent actually becomes next instead, and we can change both of these to new node. So new node dot parent, which is 3, new node become well, we're adding 3. We're at -1. I mean, yeah, we're at, this tree is wrong. Oh, it's because we were messing with it. We had 1, 4, 6. Now we're adding 3. Well, we already have the left and right ones filled. So the next one would be if we pull off the front, which is 1, then grab the front one again, it'd be 4. And then new node parent would be next. And additionally, this dot bottom rightmost nodes sub-0 dot left would be equal to new node. Now this makes sense to me. Bottom right most nodes sub-0 dot left equals new node. If it equals new node, now this makes sense. I'm wondering if this has to be symmetrical with a delete operation. Is it safe to assume we can always just shove it into the left? I think it has to, because if left and right are already set, it means the node we're at is full. So the next node, which we added previously, haven't visited yet, left child would be available. And we delete, I'm pretty sure removal of an element also takes log n time. That's because when you remove your weight from the top, it doesn't do the shuffling. From an add perspective, we didn't do the shuffling, but if we were to do the adding, we should get a tree that looks like 1, 4, 6, 3, -1. If we check the constructor, we get 1, 4, 6, 3, -1 for adding the numbers, and if we print them, let's see, that should be what we get. Feels like something is wrong. So we are back. I think if we refresh, yeah, it looks like we lost premium for a little bit. Forgot to pay. Something is off. Oh. This should say right equals new node. And the left node is this. I was trying to say is the parent would be BRMN to start. Concept properties of undefined setting this.bottom right nodes.left. Right. And then we'd have to say this dot bottom right most nodes dot push new node. So we get 1, 4, 6, and we're missing 3 and -1. Is our print function broken? Next node is 3. Does that make sense? The next node is 3, which does make Actually, that doesn't make any sense. How could the next node be 3? And the new node is also 3 when there's only one 3. need the numbers that I'm inserting in front of me. So we get 1, 4, 6. The next node should be 4. Yeah, something is wrong. Oh, no, wait. If these get pushed on, right? Right, 1, 4, and 6, right? If the BRMN is 1, how is the next node 3? Where are 4 and oh. Right. Regardless of whether or not it gets handled, where it gets placed, the nodes that we push on should end up as the next bottom rightmost nodes. I'm thinking of this, it's really a lot like a BFS, except we're keeping track of the nodes we add. Every node we add is the next node that would be the bottom rightmost node if it has no children. Now we get 1, 4, 6, 3, -1. It's exactly what we're looking for. So this is the insertion part. And then there needs to be the retaining the property part. Now we need to run all of this back. If we want this to be a min heap, you insert 1, right? And you insert 4, you insert 6. Let's just say you insert 4 and then you insert 1. You insert 4, right? Then you insert 1. If you insert 1, you have to check the bottom rightmost. We just inserted a value. And the way they said that we should do it, we just inserted 1, right? Is 1 smaller than its parent? If it is, then they should swap positions. So we could say something like, the newly inserted node would be the last node in the list. So we get the last node in the list. We'd have to check. For a min heap, we'll say while newly inserted dot parent exists and newly inserted dot val is less than newly inserted dot parent dot val. Then we'd like to swap them. Right? We'd have a temporary pointer to the parent, and we want them to swap positions. For them to swap positions, we'll save the temporary values of newly inserted dot left and dot right. Because we're going to override them, we'll say newly inserted dot left equals newly inserted dot parent dot left. And then we have one more, right? Newly inserted dot parent equals newly inserted dot parent dot parent. And then we could basically copy all these three. We're just gonna say newly inserted dot parent dot left is gonna be equal to temp left, temp right. I guess we'll call this temp parent, which would so if we change what we insert to a slightly smaller array, we'll change this to 4, we'll change this to 1, and this to 3, we should end up with 1, 4, 3. And then we'll take out -1 as a potential answer. Set properties of null setting left. Oh, I think this should say temp parent dot parent. the one above it. We'll say after and then we'll do another one. We'll say after shuffling. After node insertion, we have 4-1. After shuffling, it's borked. So if we have newly inserted dot parent and newly inserted dot val is less than newly inserted dot parent dot val. So we save all the values for the newly inserted one, left, right, and parent, which are null, null, and its parent, which is 4. Then we say its left right, what would its left even point to? it would look more like for 1, right? 1's left node one, which is newly inserted's left node, should be the parent. Dang, I feel like we lost steam. Newly inserted's left node, which is 1. Newly inserted, which is 1's left node, should be 4. So it feels like newly inserted dot left just be newly inserted dot parent. And newly inserted dot right should be newly inserted dot parent dot right. Newly inserted parent should be newly inserted parent dot parent, which would be null. Temp parent, which is now 4's left, should be where left was originally pointing, where right was initially pointing, and 4's parent should be newly inserted. I just realized a simpler way to fix this whole thing is to just swap the literal values. Newly inserted dot parent dot val, and we'll say newly inserted and we'll say node.parent.val, and we'll say node.val is equal node.val, which is the current node which has just been inserted. Its new value is going to be node.parent.val. Since we're overwriting it, we should save node.val, and node.parent.val should get the value of temp. Then we can say node is equal to node.parent. And I think now we're getting what we want. 4's parent is undefined. Right, after node insertion we have 4, 1. After shuffling we have 1, 4. After insertion we have 1, 4, 3. And if I do something crazy and I remove all the printing here, and add -3, -1, and then -300. You get -320, right? -1, -3, right? And then we have 4 and 1, and then 3. So this actually is working correctly. So I didn't think this part could be, the swapping part could be so simple, because we can just swap the values. But I think we'll stop there, and then we'll add the deletion part, which should be similar to this, and I think we should be good.